And so I want to open up everybody with welcoming you to our CCNP class, our second one this week. We are going to talk about a multitude of things today, but one of the big things I want to talk about is the meeting I had today. There was an actual online seminar for CCNP, and it was for not just Encores, actually for all the CCNPs that have been exams that have been changed. And I sent you an email talking about the different changes, and I sent you basically these two documents, or this document right here, which is where I cut a couple things out of the presentation. And one of the first things I want to talk about is this particular picture right here. This was a very good picture, and it describes what I've already told you during our discussions of the exams. And that is the depth or the level that you need to know items according to the blueprint and the verb used at the beginning. The very lowest level of knowledge is describe, explain, or understand. And that is literally, as they described it, by looking at what a white paper would say about a particular technology. So if in the blueprint it says describe this, that's the level of knowledge you need to know. Compare is considered a little bit deeper because you have to understand two different technologies and compare them to one another. We then get into construct, utilize, apply, interpret. For us, it's typically the CCNP as interpret or configure as the main verbs that are used. And you'll notice how we're getting much further along in depth of knowledge. So you've got to really know how to configure the items, how to hands-on do the work. So if there's a configure item in the blueprint, make sure you do all the labs associated with that item. All right. Then troubleshoot, identify, and diagnose. The reason this includes even more knowledge is because you have to look at outputs and making an assumption about what is broken, why it broke, what you can do to fix it. Troubleshoot is a little different than diagnose, only because diagnose means something is completely broken, whereas troubleshoot may be just one thing is not working. Also, typically with troubleshoot, we want to fix it, versus with diagnose, we're just trying to find out what is wrong. So that's a little bit different there. And then the highest depth of knowledge that they consider is design. So if anything's got design blah, you've got to know a great deal about that item. So for us, that would be designing basically the wireless LAN environment that they talk about. They then went on to show the items that had been added into the CCNP Encore version 1.1. The green items are items that are added, blue is no changes, and then yellow is where items have been removed. The major items added are describe wireless client density, which is what does density do to a wireless environment and what are some of the issues with density. We'll deal with that when we get to the wireless section. Interpreting QoS configuration, so the ability to look at a QoS configuration and say what it would do in an environment, or what its purpose is. You'll notice in the domain number 2, there were no changes. The biggest number of changes was inside of domain number 3. And you'll see here, configure spanning tree enhancements. Now they put in their spanning tree enhancements such as root guard and BPDU guard. They explained something I'd never heard from Cisco before during this meeting. And that was that if you see such as root guard or PDU guard, which by the way, if you go and look, let me go back up here and take you to the actual blueprint. I'm going to show you the actual 1.1 blueprint here. I clicked the wrong thing, sorry. Got click happy. So I show you the actual blueprint. It says in section 3 here, it says configure and verify common spanning tree protocols such as RSTP and MST, and spanning tree enhancements such as root guard and BPDU guard. Never heard them say this before, but when it says such as, that means that's not all inclusive. So you don't need to know just how to do root guard or BPDU guard. You also need to know how to do anything that's similar to root guard or BPDU guard, such as port fast, such as uplink fast, those items, other spanning tree enhancements that deal with the same concepts as root guard and BPDU guard. So that's where maybe in the past when you've taken a Cisco exam and you saw something that you said, yeah, it wasn't on the blueprint. Well, it was, it's just they hid it by saying such as something. So when you see this, that doesn't mean only know how to do root guard and BPDU guard. Know about all of the enhancements that are common with spanning tree. Okay, I want to make that clear because that caught me off guard. I never heard that in a presentation about a Cisco exam before. It was good to hear it because that clears up some things for me, definitely down the road. The other items that are in that section 3, as you will see, describe area types. So we're looking at different area types inside of both OSPF and EIGRP, such as stub areas, such as not so stub areas, such as multi-area setups. We don't have to get super detailed in OSPF, but we do need to know what those areas are. What is area 0? What is its function? Policy-based routing, describe what it is and how it works. We'll talk more about that, and we've actually talked a little bit about it. Describe wireless segmentation with groups, profiles, and tags. That's over in our wireless section coming up. And then this NTP and PTP. Now, PTP is a new protocol, PTP protocol, and it's precision time protocol. So that is one that's, to my knowledge, is not on any lab that we do, but we're going to need to at least do some research into what PTP is and how it works, so that we can look at the fact that what PTP does is it gives you more granularity and more accuracy versus NTP, so that the clocks can be synchronized. This, I really see PTP is going to be a big issue in environments with PLCs and in manufacturing environments where time is of essence. The two devices know exactly the time between them so that they know what's going on between two pieces of machinery in an environment that is running a manufacturing type environment or anything that requires extreme time sensitivity. So we will spend some time on that, and we'll look at that as we move forward. Okay. RPF check. We'll talk about that. We'll talk about what's going on there. You'll notice they removed traditional net flow configuration, but they did add a little bit about net flow in another area. We'll talk about EPOL in the security section, and there were no changes at all in automation. So overall, a very minor set of changes to the CCNP Encore from 1 to 1.1. They also gave us this. This is something brand new, never been produced by Cisco before. I sent it to you attached to the email, but it's a new matrix. It's actually an Excel spreadsheet that allows you to, and I actually told y'all to do this. I suggested you create yourself an Excel spreadsheet and that you track the individual items in the exam objectives and then put down your information. Well, you'll notice they've created one for you so that you can go in and look at these. Now, I want to show you something even cooler too. This is really neat what they've done with this particular Excel spreadsheet. They've gone into this spreadsheet, and where there is, I actually opened it twice. Again, I'm getting click happy. Actually, I opened it 3 times. All right. So what they did with the Excel spreadsheet is they went in and added where you can find additional resources. Okay. So let's say that I want to learn more about high-level enterprise network design. I can actually go and look at it's inside of the book, or it's inside of the training they have, or they've added in a place for me to be able to even go find breakout sessions from Cisco Live. So as long as you've got a cisco.com login, which all of you do because you have a Netacad login, you can actually go and click on this and download the information from that particular Cisco Live session. And so all of these resources, what are the characteristics of 1, 2, 3, and 4 tier campus? Okay. And it goes all the way down, and you can see that here are the different things that were presented directly inside of Cisco Live. Okay. So those resources are already in this particular spreadsheet. Also, if there is a some online references there, and watch it lock up on me. you can actually go and click on those. And then what you can do for yourself is once you feel like you have actually mastered that area, just put it in green. Okay, so you can mark off each one of the individual items inside of the blueprint for yourself. So this is new, completely new, and not something that's been put out before. I hope they're going to do this same thing for some of our other exams like CCNA. Did any of you open this up and take a look at it where I sent it? It just crashed on me, but any of you take a peek at that I sent you earlier today? This particular spreadsheet?
Okay. Yes, I looked at it.
It's an awesome resource for you. So make sure you make use of it. Okay. Now, last but not least, I do want to do real quickly and show you, I did put in here two different things that are really good. We went over EIGRP on Monday. There's a little Packet Life EIGRP PDF summary sheet here for you. It kind of gives you this distance vector protocol, uses dual. The internal administrative distance is 90, external is 170. Cisco proprietary, remember we said that is true, but it is actually an open standard now. They do show you the metric, so the metric formula, and they do give you the basic commands on how to configure EIGRP. All right, and so this little cheat sheet is something I dropped into the class for you so that you can have it. I've also given you a little cheat sheet on OSPF. So here's the OSPF cheat sheet. Notice that it is a link state routing protocol using the Dijkstra algorithm, uses the metric of cost, which is really dependent upon bandwidth. It is an administrative distance of 110, which it is interesting that an open link state routing protocol has a worse administrative distance than a proprietary Cisco protocol, but it does, and that's because Cisco sets the administrative distances. We'll talk about these link state advertisements today. This will give you information, and we'll talk about these types of routers and BDR-DR election and those things today. So this is just a good little PDF that you can print out for yourself. You can give it to your students. It's an excellent little resource to describe OSPF. Okay, so let's jump over and let's talk OSPF. Let's get back into where we were in our discussion of OSPF. We were about to go into the discussion on DRs and BDRs. Now, one of the things we talked about is that each router in OSPF will form an adjacency with its neighbors. Okay. Now, in a multi-access network, that means that your routers will have to create an adjacency with every other router that it can see. That could be a problem because it can cause the router to have to keep up with a large number of not only its neighbors, but also when it starts flooding out the LSD, the link state databases, it's going to have to flood them out. It's going to have to deal with all of these different pieces. And so what they did is said, let's look and let's create a system in OSPF where in a multi-access network, which is basically for us would be Ethernet, okay? So in a multi-access network such as Ethernet, instead of every single router having to form a neighbor relationship and an adjacency with each other, let's allow them to create an adjacency with what is called a designated router. We will then have them send their route table updates to the designated router and then let the designated router send it out to everyone. This way, every other router in the environment doesn't have to do link state acknowledgements to every other one. They would just LSAC the designated router. It basically makes for a more efficient use of the bandwidth in a multi-access network running OSPF. All right. Now, to do this, you've got to have a DR election. The DR election we'll talk about a little bit later, but it's going to be based upon a priority that you set, and the priority that is set on the individual interfaces. If there are no priorities set, then it's going to be based upon the router ID. And so we'll talk about that when we get there. Now, basic OSPF configuration, very simple. Router OSPF process ID, and then you put in the directly connected networks. You put in a network statement for each directly connected network. Okay, so it's not hard to do, very simple. There are ways to tell it to do every single network that is attached. You will notice that all of these particular networks in this case are going into area 0, because you do need an area 0 on all your OSPF networks. It is the most important area. It needs to be contiguous to, and we'll talk about that in the next chapter. You can also do it like this. Instead of doing each individual network, you can go into the interface and join it into an area. So IP-OSPF 1, area 0. This number would have to match the number of your process ID that you set here. So that is another way of doing it. It's the interface specific setting will take precedent over the network statement. So if you put something here that contradicts with this, so if you put in area 10.0.0.0 into area 50, and you put it in area 0 on the interface is going to override the statement that is in the actual network statement. Okay. It's a little bit difficult when you do it like this, simply because without it being centralized, it's easy to make mistakes. So we'll also talk about how to do address families and those types of things. But topology is built using that RID. And remember, the router ID is either set by you with the router ID command, the highest IP address on a loopback, or the highest IP address on a physical interface that is up. And this is, I mentioned all of this last week, or Monday. I actually mentioned that in order for a neighbor adjacency to be formed, the router IDs have to be unique between two devices. They must share a common subnet. In other words, you can't form a neighbor adjacency if you don't have a common subnet with one another. The MTUs must match on the interfaces. The area IDs must match on the segment that they're connected to. If there are DRs, it must match, and the enablement must match on the segment. And then those hello and dead timers have to be the same. They cannot be different in OSPF. And then, of course, authentication must be the same. And if it's a specialized area, those flags must be the same. So if it's a stub or not so stubby area, which we'll learn a little bit more about later, those segments would have to match. So if you tell one router it's in a stub area and don't tell the other routers in it that it's in a stub area, they're not going to talk to each other. They don't consider themselves to be in the same type of area. So here's a very simple configuration. We've got 4 routers connected with Ethernet in the center. They've all basically all the routers have loopback addresses matching their RIDs, the router IDs. That would give them their router IDs. And then you can look here. If you do show IP-OSPF interface brief, you would see the interfaces that are enabled, the PIDs, the area, the IP address, the cost, and that's been determined by the auto reference bandwidth cost, and what the current state is. Is it a DR? Is it a BDR? Is it a druther? By the way, druther means it's neither a DR or a BDR, but it could become one if it needed to. Loop or down, loop would be if it's in a looping state, which typically it's got a loop on it. And down is just down. It's not up. It's not actually seeing anybody or any OSPF neighbors. So here we look, show IP route OSPF. We can see our OSPF routes. Notice this 110 is the administrative distance. The 2 would be the cost for the route to that network. All right. That should be something you pretty much know now. OSPF has a special command. We used to call it the magic pixie dust command. It is only placed on the autonomous system border router that is going out or has the main default route that goes out for your entire network. So it's called default information originate. And what will happen with that command is, imagine if R1 is the router connected to our internet. You put the default route on it and say, go upstream to my ISP, which is at 164.1.2. Then if you put default information originate on R1, it will advertise automatically a default route to R2 that says come to R1. And then using this same information, R2 will then advertise a default route to R3 that says come to R2. Then R2 will send it to R1. You only put default information originate on one OSPF router in your environment. And it goes on the router that is connected to the outside world, the one that is the actual autonomous system border router. Does that make sense? I see people all the time put it both on R1 and R2 thinking they need it so R3 can get the information. They don't. You put it on R1, it will flow through the entire environment. Questions on that? Let me pull my chat up. I didn't have my chat up. Hey, good evening. Good. Yeah, we're doing good. Everybody's doing good. My whole department's kind of rough though. I've got this sickness I had is running through the department like wildfire. I've got people sick left and right. It's bad. So hopefully we'll get everybody back on their feet. Some common optimizations for OSPF. One is changing the auto reference bandwidth. The auto cost reference bandwidth, changing it so that a 10 gigabit and a gigabit Ethernet will not appear to be the exact same cost. By default, especially with the older auto cost reference bandwidth, the default reference bandwidth was 100 megabits, which meant that a fast Ethernet, a gigabit, and a 10 gigabit, 40 gigabit, 100 gigabit would all have a cost of 1. We don't want that. That's not good, because that will definitely affect our correct routing information. We'll see how to do that in the lab. I'm gonna actually show you the lab. Other things here are changing the hello timers and dead interval. Just remember, if you change your hello interval, you should make it your dead interval 3 times the hello. Make sure that you change this on one, you change it on all. Otherwise, you will break your neighbor relationships. Okay. If you want to see what the timers are, do show IP OSPF interface. Now, let's go to our DR and BDR elections. We probably want to control who our DR and BDR is because we want our router with the most horsepower, the most CPU, the most RAM to be our DR. And then we want our second most powerful router to be our BDR. We can control this with OSPF priority set on the interfaces. By default, the priority on all interfaces is 1. Okay. So if you don't do anything, nothing at all the OSPF priorities stay the same of 1 on the interfaces. That means that the RID, the highest RID ID, becomes the designated router. The second highest becomes the backup designated router. So again, you have to be very careful with that. Now, you'll notice this environment right here. If we had, let's imagine we didn't set any RIDs, so we're not going to set any router IDs. We did not change the priority. Ignore where it says always DR and always brother. Looking at this picture right here, if nothing else changed, all right, and so this is, let's say gig 01 is 123.4.1, and then gig 01 here is 4.2 on R3. Actually, let's do 2 on 2, 3 on 3, 4 on 4. Who would become the DR if we did not have any router ID set and we did not change the default priorities on this right here? Again, ignore always DR here and always brother here. Put your answer in the chat. Which one do you think would become the DR? Drop your answer in chat or come off mute and just tell me what you think it is. So, where's my little, let me find my pad here. Hold on just a second. I hadn't used this in a while. You got to get it pulled up. Anybody there? Y'all awake? Are you with me?
I'm here.
Earth to class, Earth to class.
I'm here.
Okay. So let me pull it up here. I'll drop it into my whiteboard so I can show you what I'm talking about. I'll pull it out and hold on a minute. My whiteboard's giving me, of course, giving me trouble. Oh, you got to be kidding me. There we go. Okay, good. That's good. All right, so I'm going to cut this picture out. So I'm going to come over here with my snipping tool. I'm going to cut this picture out right here. Control C. Control V. All right, so now that I finally, all that work to get this one picture over here on the screen. So let's assume, let's go ahead and say, all right, we do not have, this is not here. Just ignore that. Ignore this. This is 123.4.1 right here. This is 4.2 right here. This is 4.3 and 4.4. Okay. First off, tell me, what would be the router ID of each one of these routers? We have not set a router ID. Okay, so I said we didn't set a router ID.
The highest configured IP address.
Correct. So for R1, its router ID would be 10.123.4.1. R2 would be 4.2. R3 would be 4.3. And R4 would be 4.4. So if nothing else was changed, no priority was changed, nothing was to take place, who would be our DR? The designated router. It's gonna be the one with the highest router ID.
That'll be router 4.
Correct. That is correct. So with nothing changed, our DR would be router 4, our BDR would be router 3, and these would be what are called druthers. Okay, so they could be a DR if needed be. All right, the druther. All right. Now, however, what we're going to do is we're going to change this. We're going to make sure we control who becomes the DR. To do that, all right, we do the following. We go in here and we can set it if we always want this to be the DR. Okay, so we always want R1 to be the DR. We would simply change the priority on this interface to be greater than 1. So let's say we set it to 100. And if we wanted this to be our DR, we would set this to some number above 1 but below 100. So we set it to 50. Now, what if we didn't want it? If we wanted a router to never participate ever in DR or BDR election.
Priority of 0.
Exactly. Set the priority to 0. So we can say that's a 0. Leave this at 1 with a priority of 1. And this could be a druther if it needed to be. Okay. So that's how we control our election. So in this case, we went to R1. We gave it a priority of 100. All right. We went to R4. Now, when it says priority of 0, I actually disagree with what they're saying here is always druther. No, R4 will not even participate. It will not be a DR or a BDR. It's not going to actually participate at all. All right. Where does this election take place? It takes place on broadcast networks. Okay. Broadcast networks, we have BDR and DR fields. All right. Non-broadcast multi-access, they are also available there. That's where a DR and BDR election can take place. And non-broadcast multi-access are frame relay interfaces, frame relay sub point-to-point and point-to-multipoint interfaces. We really don't even study frame relay anymore, hardly ever. But just realize there are DR, BDR elections in those environments. You can also see the default timers. On a broadcast network, it's 10 for hello and dead of 40. We've got on point-to-point 10 and 40, on point-to-multipoint 30 and 120. Okay. Other types of networks, obviously broadcast networks are those that can have broadcast point-to-point or point-to-point. We know those. And a loopback network is it's enabled for a default loopback interface. It was loopback has a /32. All right. And you've probably seen that advertised before, a loopback as a /32 instead of a normal /22, /21, /24, whatever. Okay. Now, what I want to do is I want to jump back over to NetLabs, because what I have done at this point is I have actually gone in and prepared this lab right here for us, implement single area OSPF. And so I went in, and by the way, whenever I do a lab, the first thing I do is I erase the VLAN.dat and I delete the startup config and I reload the switches. Even if it's a brand new reservation, I did that on all of these. So all of these have actually been reloaded and brought up. I also have gone in on all the PCs and put IP addresses on the PC interfaces. Okay, on that VNet bridge.
Excuse me, Kelly. Would that be our procedure from now on? Because yes. I don't do that.
Yes, I would on every single one of them. I go to even if it's a brand new reservation, erase the VLAN.dat, erase the start, delete the VLAN.dat, erase the startup, and reload it.
Okay.
Then I went in and using those files that I gave you, which I've shown you before, I pasted in the configs. So the configs have been pasted in, these default configs that are inside of the lab here. So I'm actually all the way down to this section right here. I'm actually going to pull that up so I'm going to pop this out in a new window. So I'm going to put this over here, and I'm going to put my NetLabs, I can find it right here. Okay, so I've gone in and I've actually tested my pinging from 10.10.02 and 10.10.03. I have successful pingage from inside of R1. So what we're going to end up doing is we're going to configure OSPF on D1 using explicit IP addresses. So it's really a very simple process. All we're going to do is we're going to go into config T. We're going to do router OSPF 123 in this case is the process ID they wish to use. By the way, process IDs do not have to match between OSPF peers inside of EIGRP. Remember, one of the things in the exam directives was to be able to compare and contrast these two. With the EIGRP, the autonomous systems must match in order for two EIGRP routers to talk to each other. Does not have to match in OSPF. All right, now the area has to match, but not the actual process ID for it. So I could do OSPF 123 on D1 and OSPF 456 on D2, and it would still work. Now it's a dumb idea because you really should have them match so that you understand they're in a relationship, an OSPF relationship with each other. Okay. Oh, IP routing is not enabled, so I forgot to turn on IP routing. So let's do IP routing, which by the way on a switch that makes sense because it's not on. Hit the up arrow because I'm lazy. I mean efficient. I'm efficient, not lazy. So now I'm going to enable the interfaces network 10.10.8.1 0.0.0.0 and put that in area 0. Hit the up arrow to be efficient and change this one item to 9. And now those two networks that are on, if I do a show IP int brief, you'll see the two networks. Actually, all right. Do show IP int brief pipe include. Let's see if I can do it this way. Yep. So you'll see that the network 10.10.8.1 and 10.10.9.1 have been placed. If I do a do show, and notice what I'm doing, folks, the lab tells me to do a show IP protocols. I don't even drop out of configuration mode. I just use the do command. Do show IP protocols. We will see that OSPF is running, process ID 123, and we are routing for the two networks 10.10.8.1 and 10.10.9.1. All right. Now, you'll notice I also forgot to do one. I forgot to do the very first one. So I just hit the up arrow twice. Fix that 10.10.02 and 10.0.2. And the reason we use the quad zeros is because it basically says advertise the network that is on that interface. Okay. So it takes the subnet mask that's on that interface and it will automatically put that with the route table updates. So I'm now advertising those three networks. If I do a do show IP protocol, you'll see those three networks are being advertised inside of OSPF. Pretty simple, actually very simple. Now we can also do this with wildcard mask. So we're going to go over to D2 and do it with wildcard mask. So we're going to go config T, turn on IP routing. We'll do router OSPF 123. Then we're going to put in the network using the actual wildcard mask 10.10.0.0.0.0.7 area 0. And then we're going to do two more here, and I probably should have just retyped it, but notice we just got an adjacency. So we just loaded an adjacency there. So 10.10.24.0.0.0.255 and hit the up arrow and do 25. All right. Now, if I do a do show IP protocols, you should see that I'm advertising for those three networks. So simply two different ways of doing it. One is telling it advertise whatever mask you placed on the interface. The other one is doing the full wildcard mask as it relates to the actual interfaces. I can do this now too. Do show IP OSPF neighbors. And I can see my neighbor. I've got a neighbor on 10.10.9.1. And you'll notice a full DR. So my neighbor is the DR. So I would be the BDR more than likely, since there's only point-to-point link in this particular case on this one. All right. So we could have used this statement, and that's just telling you if you were to use the summarization to get both networks in there, you could have done that. Pretty easy. And then we're going to go to R1 and use the interface specific method. So it's just showing you different ways to do it. Notice we don't have to turn on IP routing on the router. It's already on, okay? So we can go interface, loop back, 1. We're going to do IP OSPF type of network, actually network, point to point, oops, point to point, because it is a point to point link. All right. Then we're going to do IP OSPF 123 area 0. And that assigns a loop back into area 0. Then we're going to exit back out. Actually, we can just go straight over. We don't have to do it this way. Int gig 000. Clay, you say you have trouble with the pipe command. With my hands now, I have trouble with that slash. That slash right there drives me nuts with my hands now. It used to not bother me, but with the way my hands are now after my injury, it drives me crazy. Notice now we've got a relationship. If I do show IP protocols, pipe section, OSPF, you'll see that I have OSPF, and you'll notice that I am explicitly routing for the loopback and for the gigabit 000. So 3 different methods to configure OSPF. They all work. Okay. I do show IP OSPF neighbors. You see now I've got 2 different neighbors, one on each of the 2 links, the 9 link and the 25.1 link. Okay. You'll notice too that my router ID ended up being the highest loopback address on this particular router. Now I'm going to change the router ID, router OSPF 123. I'm going to get a router ID of 1.1.1.1. Now, one thing that'll happen is you have to clear the IP OSPF process in order for it to actually change the router ID. So if you do show, I don't have to do here, do a show IP protocol, you'll notice my router ID is not changed yet, or will not change. It's still this 200 until I do a clear IP OSPF process. And you do hit enter, yes, and everything will go down. You'll lose your neighbor relationships. They'll come back up. You hit show IP protocol now, and you will notice that the router ID changes. So unless you clear the OSPF process and basically force it to do a new calculation of the router ID, even if you change the router ID after you've started the OSPF process, it will not take effect until you reset the process. Okay. So let's go over on D1 and change this. So router ID D1 should be 2.2.2.2. Let's do it. Do clear IP OSPF process. It's going to say sure, yes. All right, so there we go. That should reset that. And D2 router ID 3.3.3.3. Do clear IP process OSPF. Notice I love the do command, folks. Clear IP OSPF. I spelled it wrong. Did it backwards. OSPF process. I love the do command because it saves me time. Faster we can do things, the better off we are. So I go to R1 and I do a show IP route OSPF pipe, begin, gateway. Gateway. Go IP route. SPF. We're waiting for it to come back up. There it goes. Yep. Took a little while. There we go. There they are. So now we can see the 8.0, 9.0, 24, and 25. So those are the 4 networks, 2 learned from D1, 2 learned for D2. Okay. That's got us all of our different routes that we have there. Same with D1. We should have do show IP OSPF. Show IP route OSPF pipe begin gateway. All right, and there we've got our 3 routes, 24, 25, learned from D2, and the route that has been learned from R1. Okay, so very, very cool. We also can see in R1, I do want to show you this command, show IP OSPF interface brief, because it can show you the area that the particular interface is part of, the mask that is on that, the IP address and mask on that interface, its current state, and what it is in terms of druther or that. And it also shows you the cost associated with a particular interface. So folks, this is a very easy lab here. I do want to quickly do this. I want to go ahead and do it. Show you the default information originate. So if I do an IP route quad 0, so I'm putting the default route on R1 and saying this is the way to get out of our network. Go to loopback 0 to get out. Okay, and I know you get that. It's just part of it, but because you're using a loopback as a simulated default route. Now we're going to put default space information origin. Oh crap! Default information originate. All right. Now you'll notice what happens is on D1, if I do an up arrow and show this, look at this. We now have a new route. We have a new OE2, which means it's an external route. This is a route that's been injected into OSPF from an external process. And it tells you that this is a quad 0 route. So this, the minute I see a star E2, that tells me it's been injected by default information originate. And you'll notice, look at this, go to D2 and issue the same command, show IP route OSPF pipe begin gateway. Oops, show IP route. Here, let's just do this. I'll drop out.
Do.
It's just easy to do this because there's nothing really on here. But look, here's the OSPF right there again. That's that default route. And if there was another router below D1 and there's a router below D2, those routers would have this same OE2, but instead of pointing up to R1, it would point upstream to the next router in the upstream link. You only have to put this on one router, the one that is your autonomous system border router, the one going out. Questions? How many of you have done 812?
I have.
Okay. It's a good, very, very good lab. Make sure you do it. Make sure you complete all these areas here too, because I'm not going to go through this link cost and all that, but you'll notice the auto reference cost is typically 100 megabits per second. You need to change that if you want to be able to make it where your reference cost is accurate. If you, one of the things here, oh, go ahead.
In the documentation, they mentioned the difference between E1 and E2.
E2, it's a different type of external.
Yes, but I'm saying it was missing from the documentation. My voice is bad.
Okay.
It's not necessary. It's not necessary, is it?
No, it's not, but I mean, we can look at it a little bit. The typical way that you describe, they're both external routes. Okay,
Yeah.
an E1 and E2 route are both external. E2 routes only give you the cost to the ASBR. The direct cost from the E2 route reflects the cost from the ASBR to the destination. Okay. If it was an E1 route, it's got the cumulative cost to reach the destination. So if it was an E2, an injected E1 route, it would actually bring in the cost of the external route with it. Whereas
Yes.
the E2 route is only showing the cost of getting to your autonomous system border router. There's a pretty good discussion. Let's see. Here, I can give you this document right here. There's a good discussion of it. Well, that went to the wrong place. Of course, they'd have to move my document. Let me see if I can find that discussion. Okay, here I'm gonna paste in the chat. I'll drop this in chat, and I'm also going to pull it over to our thing here. So here's an example. When you look at E1 and E2 routes, when you look at E2 routes, E1 is the cost of the external metric with the additional internal cost to reach the network. So what it would do is, if let's say you brought in an EIGRP route, it would have to, it has a method where it takes the EIGRP metric and converts that into a cost. And it will then bring that in and add it together to the cost that it takes for you to get to the ASBR. And that will be the entire cost of the autonomous system border router, or that particular E1. Okay. E2 routes only hold the costs as they are related to getting to the autonomous system border router. Now, we get into a little bit later talking more about these not so stubby areas and autonomous system areas and external routes, but for what we're doing right now, E2 routes are what is shown when the default information originate. So again, if you're asked, it's the internal cost to the ASBR added to the external cost, whatever it happens to be. E2 doesn't give you the external cost. It's only the internal cost to get there. So it's a different way of bringing the route in. Does that make sense?
Yes, it does.
Okay. All right. The rest of these items here, again, you can change hello and dead timers. Only do that if you're really instructed to do so. But since they're telling you how to do it, and they do show you how to do your DR placement here. So you go in and change the priority on different interfaces so that you have the election that you want. So very good lab. Not a very difficult lab, but it's a good lab. Okay. I'm gonna do any questions on this lab before I end it. All right, so I'm gonna end that reservation. Remember, if you get done with the lab and you're not using it anymore, end your reservation. Don't keep it open, because it is actually kept open and your classmates cannot use it. So let's move now and look at a little more detailed or advanced OSPF. So OSPF has the ability to be split into areas, and those areas are used to maintain and keep flapping links, routing table updates, link state database updates, link state database recalculations, to keep them inside of an area. So we're going to look at link state announcements. We're going to look at how areas work. We're going to look at what you shouldn't do, which is a discontiguous area 0, which you should never have. But first off, areas are a logical grouping of routers together. Now, they tell you that by default, a flapping link won't cause problems or cause full SPF recalculation, which is true between areas. But it is also true that by default, unless you change it, every network that is in one area will be known about in other areas through what's called a type 3 LSA. It's a network LSA. And we'll talk about those. But you can change that. You can actually change it to where it only sends summary addresses or summary information instead of the full information. So just be aware that that is important. The big thing though is inside of an area, if a link drops and there's a type 1 LSA goes out, Everyone else within that area has to run the SPF to get a new calculation. If you won't have that if you're not in that area, okay? The other problem with areas is this: if you put too many routers in an area, the link state database becomes too big and unmanageable. It takes more memory, it takes more SPF computation to do that. And within areas, summarization doesn't occur. So what we want to do is, when we design our networks, we want to design them so that we can have IP addressing schemes to make each area its own summarized block. What we do on our campus, by the way, is each building is its own OSPF area. And those buildings are summarized to a block of addresses, so that in the core, there's one or two at most routes from our core to each building to keep things in check. And so we actually have routed network between our buildings here on campus. We don't do layer 2 out to the buildings. We do layer 3, which reduces the number of broadcasts, reduces all kind of problems of spanning tree. It keeps spanning tree inside of the buildings. And it really allows us to have a more efficient core network, because we have what, 10 buildings on campus. There's 20 routes in the core, 20 to 25 routes in the core. So by default, you'll see that it hides topology from the other areas, but it's not really accurate to say that these routes don't go between the areas, because by default, they actually do get advertised. The routes get advertised as type 3 LSAs or network LSAs between the different areas by the area border routers. You can change that. You can summarize, but it's still going to be advertised. The most important area is area 0. It's called the backbone, and all OSPF networks must have an area 0. Any router that connects to area 0 in another area is called an area border router, because it borders two different areas. ABRs are responsible for taking the type 1 LSAs, type 2 LSAs inside of them and converting them into type 3s and moving them between areas. So you'll see that the routes do get sent in between the different areas. Here we have configuration of on R4, it's a member of both area 0 and area 1, 2, 3, 4. The other areas, hey, yeah, come on in, you grab it. The other areas are part of the area 56. You'll notice that's R5 and R6. So in this instance, R4 would be an area border router and also a backbone router. R5 would be an area border router and a backbone router. R6 would be just a router inside of area 56. Thank you. Have a good one. And then R1 and R2 and R3 would also be what are called inter-area or intra-area routers only. They'd be inside that area 1, 2, 3, 4. All right. So area ID can be, it can either be a decimal number or a dotted decimal. Have any of you ever seen somebody use dotted decimal for their area numbers or area IDs? I haven't. I haven't seen it out in the real world, but I mean, I guess you can. Okay. I didn't think that was very common out there. So intra-area routes are routes within the area. So IA routes are intra-area routes. And then inter-area routes are routes in between areas. Okay. So you'll notice if you look in a routing table and you see OIA routes, those routes are in between the areas, and the intra are O routes. So those are the OSPF routes. So intra is within, inter is IA. Okay. So inter-area routes, that would be between different areas. And that makes sense. If you look in here on R1, R1 would have the routes for 1, 2, 3, 1, 0, 3, 0. Those are within in the intra area, whereas the 45 and 56, those are going to be inter-area or in between the different areas. So that tells you they're external to R1. Those would have been learned, by the way, from R4, as a type 3 LSA that was brought in from the other areas. You'll notice too, we've got our administrative distance of 110, and we've got our cost. And that is the cost of the links in the path to that particular network. Okay. Excuse me. So for R1 to get to 1033, it's cost of 66. For it to get to that's R4. For R4 to get to 123.1.0, it also has a cost of 65. So it tells you the different costs to get to those items. Now, area R4 doesn't connect to area 56. Okay, so you'll see that is a inter-area route. All right.
Mhm.
Inter-area route there. Now, again, just showing more of the routing tables. You can, and again, remember, you can actually inject external routes into OSPF. You can do that with that default information originate. You can also do it with redistribute static. You can do it with redistribute other routing protocols. So there is a way you can bring in other routing protocols into OSPF. They will be external routes, so they'll be E1 and E2s. So how about these link state advertisements? What types do we have? There's actually more than this, okay? But the ones we're going to focus on primarily are these 6. There's a type 1, which is a router LSA. And this is every router in an area advertises its directly connected links as a link state. So those are link states. So link state advertisements, type 1 router LSA. Type 2 are, these are the network LSAs that take place in a network segment attached to a DR. Okay, so remember, if we don't have a DR, everyone has to send out type 1s and everyone else has to acknowledge them and deal with them and form an adjacency with everyone else. Well, in a multi-access network with DRs and BDRs, we end up with a DR, and all the type 1s go to that DR, and then the DR turns around and sends those back out as a type 2. That is how it actually grabs all the information and becomes the central point that sends out that information in a multi-access network. Type 3s are called summary LSAs. That's where an area border router takes the network prefixes it learned from both inside its area and sends it external, and external ones it learns and sends them internal to the area that it's part of. So basically, it's the go-between. And by default, all networks that an area border learns about, either in its one area on, area 1, 2, 3 or area 0, it's going to share between those two areas. So they will be known. You will have full information about all the networks. You just won't necessarily have route flapping, because you won't have to deal with every single router LSA. The ASBR is a summary LSA if you have an autonomous system border router. We'll talk more about those later. And then we do have type 5s, which are external LSAs. Those are ones that have been brought in externally. Those are the E1 or E2s. So technically, the default information originate is a type 5 LSA that's brought in by an ASBR. And then last but not least, we also do have what's called a not so stubby external LSA, and that's advertising redistributed routes into not so stubby areas. What does an LSA have? Well, it's got its age, how long it's been flooded, the sequence number for it, what type it is, and then you'll notice here, again, every OSPF router advertises a type 1 LSA for every link it has, and that is the essential building block of link state databases. So as each router in an area gets these LSAs, it's going to add that information to its topology database, and that's going to be used to build the shortest path first. But notice type 1 LSAs do not go across an area border router. Okay? So these are not advertised outside a single area. Type 1s are not. Type 2s are LSAs and multi-access networks where the DR has pulled in all the type 1 LSAs, all right, and then sends them back out as a type 2 LSA. All right. So be aware that that's how it deals with keeping each router from having to create an adjacency with every other router in a multi-access network. Type 3s are LSAs that have been brought into, type 1 LSAs have been brought into an area border router that are then converted into type 3s to tell other areas about the networks inside of the areas that that border router is a part of. So R4 will tell area 0 about the networks in 1, 2, 3, 4 using type 3 LSAs, and vice versa. It will take the type 1 LSAs it learns from area 0 and send those over as type 3 LSAs into 1, 2, 3, 4. It will also take the type 3 LSAs that come from area 56 to R5 and get sent in area 0 and will forward those. So you'll notice type 1 LSAs are used to create the type 3 LSAs that are sent to R4. R4 sends them to R5. R5 sends the area 1, 2, 3, 4 type 3 LSAs over to R6, and then vice versa. To me, this slide is the best slide to kind of show how OSPF works unless you modify it. Everyone's going to know about every other network, okay, every single link. So even if a link does go down, there's still going to be a type 3 LSA that gets sent across the network and forces a change in the database unless you do a summarization between your areas. And that's really the main reason to do areas, is to do that summarization between them. Now, if a router for a type 3 LSA is the last ABR to advertise the prefix, you'll look at some of the metrics here. The type 3 LSA is created from a type 1. It's the total path metric to reach the originating router in the type 1 LSA. If a type 3 is created from a type 3 LSA from area 0, total path metric to the ABR plus the metric to the original type 3 LSA. So in other words, it adds in the metric for the entire distance across there. So you can see your total metric here is 2 going across because of the fact that it was brought in from an external, from another area for R4. Let's see here. What time is it? Oh, let's go ahead and talk about real quickly about discontiguous networks, and we'll stop. Here's the biggest thing, folks. You should not have discontiguous networks. And by that, I mean this. Area 0 should never have an area in between it. Also, by default, the rule is all areas connect to area 0. So every area would have an area border router at area 0. We're going to learn about a virtual link. There's a way to do this in an emergency situation. It's not really a preferred configuration, but in an emergency situation, you can create a virtual link for an area that for some reason is not connected to area 0, but it is not preferred. If you have discontiguous networks, you can really get into some serious problems with your LSAs, and you can end up with routing tables that are summarized incorrectly and are just that you're going to have a mess. What you're going to have. Okay. Simplest fix is just make sure you don't have discontiguous area 0. You also can do GRE tunnels to fix this, to make them think they're connected to area 0. And you can do what is called a virtual link. And we'll talk more about that later. Okay, everybody, I'm going to stop here. We're going to talk about path selection next week. Are there any questions? Please make sure you look over this OSPF, the EIGRP PDF, and look over these 2 items I left up here for you, this learning matrix and this WebEx doc I left for you. Okay. Take a peek at those and bring any questions you have. And also remember, everyone, if you don't mind, I need you to log in to canvas.stanley.edu at least every week, let's say on Wednesday, so I can do attendance. That is a new item that's been required for us now in the state of North Carolina, that you are attending, and we're doing weekly attendance. So if you will, make sure you log into canvas.stanley.edu today or tomorrow at the latest, so I can do attendance for you this week.